what's your take on control system for robotics and other industrial applications? As a student of robotics, where should we start with the control systems? How do you look at things? Because whenever we open a book of control system, there is the language and jargons of how do you look onto machines and robots?
The faster you make your response, the more noise from the sensor.
Bachelor's, master's, and PhD in control systems.
I don't really care about the certification. So I don't think degrees make you better because you have the piece of paper.
Here we have control engineer team manager Simone Bertoni. He works at Ceres, and let's find out what he has for us today. Hi, Simone. How are you?
Hi, Lukman. I'm very well, thank you. Thanks for having me.
I have gone through a lot of your posts about PID control system, and it's quite interesting. I have been into robotics on the autonomy side, software development, and now I'm finding the need of control system. It is very important and it is inevitable. You cannot ignore it. So what's your take on control system for robotics and other industrial applications?
Yeah, I agree. I think it's very important. And I believe in robotics, you can have applications where you don't know there is control systems doing something under the hood, but there still are. So I'm not an expert in specifically robotics. For example, if you think about robotic arms, in some applications, you can probably just tell the position you want the joints to be at, because you have servo motors and something that is assisted that is doing the job for you. So you can do your direct or inverse kinematic and define your trajectory, find the job where you want the joints to be and how you want them to evolve. You pass that to them, but the reason why that works and you can not think about controls is because someone else has done it for you, because there are servo motors that are doing that job for you, right?
Okay.
Similarly, a lot of mobile robots where you have wheels, you can probably tell the wheel to spin at a certain speed, right? So you don't really care. I think for mobile robots, you probably need to care to control the direction and the speed anyway. Still, there is a lot more than what you see if you develop at a slightly higher level there, right? So there is all that layer of control that is hidden to us, but it's still there. So if you take away controls entirely from robotics, what do? You probably move things in open loop, like in the Industrial Revolution, maybe, right? So you could do a bit of very simple automation, but you move actuators, you have to wait for them to hit something maybe and stop them there, but there's no real control of position or speed or anything.
Total chaos.
Yes, I think so.
There is control on the hardware side, there is control on the software side. So mostly we will be talking about control on the software side, steps towards it. What in control systems of software side, we have a lot of things and they affect the robot's behavior a lot. So what do you think about in a mobile robots? If we start as a student of robotics, where should we start with the control systems?
I think you need to start from the basics always, right? So you study all the linear control theory and PID stuff and related stuff, and you give yourself a good solid foundation. And my suggestion generally when we have to learn something is that we need to practice, okay? Whether it is in hardware stuff, so with real robots in this case, or in simulation. We can also practice in simulation, okay? And what I mean is you are studying linear control systems. So you build a model, a transient model of your system, and you try to apply the theory that you studied. And you do your simulation and you try something. You try to change the numbers. You see how it responds. Then you're learning a slightly new controller. You do it again and you do it again for that slightly new controller. But this process is important, and I think it's easy to overlook it, because a lot of times you find examples in books or courses or whatever. So you read the example, you understand it, it works, it makes sense, and you go ahead, right? But that's the example that someone else has made. And it works, it's there to work, it's been put there to work, someone else has tried it, but you haven't really understood it. So I think you should do your own, slightly different, and make it work. I think that's incredibly
From software to hardware.
Yeah, in both cases, in hardware, you have to do your own anyway, right? Because if you're studying a book, you will not be provided with the hardware that works with the example. But even in simulation, you have to build your own things and play and play and play and have your fun, hit your walls and turn around and until you really understand it. I think that's the real thing.
Okay. So starting from this perspective that control system is always considered to be a part of robotics, but control system is a subject that comes in robotics and all machines wherever we need smooth behavior. So from a control system perspective, how do you look at things? Because whenever we open a book of control system, there is the language and jargons of plant and things like that, state responses, all of these. We'll go in detail on these jargons. But when you, from a control system, how do you look onto machines and robots?
You look at them as dynamic systems, like everything else, fundamentally. So essentially, the process that you normally go through if you have to design something completely new is you model your system, and I mean modeling in terms of transient response, right? So transfer functions, that sort. Then you have probably some requirements. You want to have some kind of overshoot transient response. You have some requirements. And you translate that into requirements, probably in frequency generally. From there, you synthesize your controller, which could be a fixed structure. So you might know that you want a PID and you can't really move the structure from there, or maybe you're more free and you can have any linear controller. And then you get out a controller for that specific system.
Okay.
From there, next steps, if you want to go all the way to the hardware, my process would be, at this point you have done the very minimum, right? So purely control. Then you have to build a proper model of your system, which is probably non-linear. It could be done in tools like a causal modeling, right? Like Simscape, for example, that sort of things.
Let's, if you don't mind, if we just fix an example, it would become more easier, right? So let's bring in a mobile robot that has a encoders that tells us about how much wheels have rotated, and with that information we are going towards a goal. So can we work on this and go through a whole process?
Yeah, okay. So what are we controlling? Are we controlling the speed of the robot?
Yes, speed of the robot.
Okay, so let's say if we are doing this example, the first thing would be you model your system in a linear way, probably. In this case, it's easy to model the system in a linear way. You have basically two states, the position of the robot and the speed of the robot, okay? Your dynamics are probably the torque that you apply to the wheel divided by the radius, I think, something like that, to translate it into a force on the x-axis if we have only one axis in this case. And then you have some friction that is counteracting that, right? So you have first order response from the torque to the speed, and then you have an integrator for the position of the robot. If you're going to ask something, go.
No. I was saying okay, because these are a lot of technical things.
Yeah, I know. But yeah, let's say from there we get a transfer function that is it's probably a simplification, okay? We haven't modeled many things like the encoder resolution. At this stage, we haven't modeled the fact that the encoder is it's definitely in discrete time. We're not doing that part for now, okay? So we're doing a simple transfer function. We got our transfer function, our dynamic response. From there, we get our transfer function. From our transfer function, we say, okay, these are our requirements. So, for example, we say we are controlling his speed. Now I'm making up numbers totally here, okay? So we are controlling his speed. We probably won't have, I don't think we would be desperate if we had some overshoot. It's not the end of the world, but probably we want to not too much, right? So 5% overshoot, no more than 5%. We define overshoot as if we are aiming for 1 meter per second speed, for example. We don't want to go beyond 1.05. Okay, no more than 5% the set point that we are aiming to a step response. If the set point we generate goes up to 1 instantaneous, okay? So that could be a requirement, for example. And then another requirement might be that the rise time, which there are various ways to define it, but it could be the time you take to get to 90% of the set point. It's a measurement of how fast you want to get to the set point, right? So you can have something around that, which is, I don't know, 1 second, making the numbers up completely. Another thing might be disturbance rejection, especially disturbance on the sensor, okay? So in this case, we have a sensor that is measuring the speed, okay? We can say that we differentiate and we filter that signal to estimate the speed of the robot, okay? So we filter the encoders and we make a speed out of it. That speed will have some noise, right? Which is probably higher at higher frequencies and lower at lower frequencies, possibly even nothing, okay? That disturbance is going to go back on it's an interesting compromise there that you have to strike between the faster you make your response, typically the more noise from the sensor you take into the actuation that you give to your wheels in this case.
Okay.
And then the other thing is you definitely want some sort of steady state error when you control your speed, right? Presumably you don't want any steady state error. That could be a reasonable ask, I think, in this case.
The information that you have provided is not everything that you would do, but it's something that you should consider when starting, right?
Yeah, I think everything is really difficult to just improvise everything and talk about everything, because it's very also dependent on the requirements that you have.
Whenever you talk about dynamic systems modeling, so what do you think about this? We are talking about the motion of the robot, that's one thing. Wheels, motors, everything, and sensors, even all of these things are modeled when we are working for industrial applications?
You have various ways, I think, to tackle that. It really depends on how much you think these parts will affect the overall response. You can model the system, like we said, ignoring basically the sensor and ignoring the dynamics of the wheel, because you think in an engineering way, okay? So you think with some backing, right? So you know that have done your calculations and you think it affects not too much. So it's negligible. For example, the sensor is extremely fast respect to the dynamic you are aiming for, and you think it's basically negligible. So you could do that. That's probably often the case. Your wheels might be DC motors, might be brushless motors, maybe. You have a current as well, right? So you have an electrical characteristic of the motors. Do you want to control your robot to be so fast that you need to count for that part, or you can decouple the two things entirely? So let's say we carry on that example. We have our simplified model, and one way to do it here, because it's simple, could be you take it to the root locus, for example. So we have our error between our set point and our speed. This goes through a controller structure, then goes through the plant, which is our mini model that we described. This whole structure, including the feedback loop, it has a new response, right? It's another dynamic system in the sense of transfer function, okay? This transfer function, so that goes from the set point to the speed of our mobile robot, has its own poles. How do these poles move on the real imaginary plane if you vary the gain that you have in your controller? This is the root locus.
And what does it affect?
It affects the final response of the closed loop system.
Okay.
So by doing that, you can decide where the poles of the final system will be, which means how fast it will be, whether it will be stable or unstable, and how damped it will be.
Okay.
So imagine that you have a curve in this imaginary and real plane, okay? So the x-axis is the real part of your pole and the y-axis is the imaginary part. By tuning your your gain on your controller, you see where these poles go from when you have no gain to infinite, fundamentally, okay? And you see how they move. Bear in mind that you haven't complete freedom, okay? Because these poles move constrained on some axes that are the root locus.
Okay.
So you can decide how you go along these axes if you want these curves. So if you go more ahead towards the curve or you go less, but you can't really go wherever you want in the plane. You need to stay on the root locus.
Okay.
So if you have an example here could be, with a bit of experience, we have the feeling that probably PI controller would work very well.
Okay.
And the reason why I say that is intuition probably tells us that we need some integral control, okay? And the way to think about that, if you think about your robot is going at the speed you want, your error is zero. Because if it is being controlled, your error is zero.
Okay.
Your derivative of the error would also be zero because it's a steady state.
But changing.
So if you don't have any integral, your torque will be zero, right? Because the output of the controller would be zero. But if it is zero, you can't be going at the speed you want if you are on a plane, right? On a flat surface. So that's a way to say, okay, intuitively, I definitely need an integral because otherwise I will never really get to the right point. Does that make sense, you think?
Yes, that makes sense.
Okay. So if you say that we have defined that we try a PI, okay, we put our PI controller with a proportional starting point and an integral gain a starting point, that will give us a certain root locus. Okay, so we fix the structure of the controller and we can tune the gain that we have in front of everything. So as this gain increases, we will increase both the proportional and the integral. Okay, if we do this root locus analysis, okay, that's one way to do it. And we will see that how the tuples that we have in the system will evolve with increasing this gain. Okay, so the tuples of the final closed loop system will evolve. And you will see that they will start by staying on the real axis, which will give you a non-oscillatory response, and then they will start going on the imaginary axis. I'm doing this in my head more or less, okay? But I think it's a relevant example, and maybe the people that are listening could try to reproduce this. Maybe we can give a hint of a mini example at some point for people to try. And the way these poles are on the imaginary axis, so how big the imaginary part is respect to the real part, in this example, because it's a second order, can be directly linked to the overshoot. So by saying we want 5% overshoot, we have basically said the maximum, the minimum damping we want on the final closed loop system.
Okay.
Then the rise time is also correlated to where you place your poles. And this is more correlated on the how far left they are on the plane, because they need to be bigger. The bigger they are in module, the faster the final response will be. If we talk about it without any whiteboard or anything, it gets very complicated very
yes.
quickly.
So I think it is very important also to understand that this process is not simple. What people have in mind when starting out, that we want to achieve a velocity of 2.5 meters, or let's say 0.5 meter per second on a mobile robot. Then we can apply proportional controller, that is getting the error, just subtracting and getting the error. Once they get the error, and that's it. If they want a quicker response, what they will do, put the value of constant a little bigger or smaller, and then overshoot. Mostly people don't care about overshoot. Now coming to this point, obviously these are hobby projects. Coming to the more professional domain, PID is very popular and it is very powerful as well. So how do you find your constants? What is the appropriate way of not just giving these values and getting the results and observing? Is there any proper formal way?
It's a good question. So there are formal ways, as the old school Ziegler-Nichols, for example, or there are other approaches which are experimental. And they are very designed, because they are oldish ways, they are very designed on industrial examples, on processes. So they're designed to be done on a process that is now being controlled. You probably don't want to stop it. So you have the real thing going, okay?
Okay.
You probably don't want to stop it, but you don't mind perturbing it a little bit. So these methods generally are about starting from a proportional only. You increase it until you get a permanent oscillation. The more you increase it, the more you get this thing, right? So you don't want to, if it exhausts, you don't want it. It's too little. If it goes unstable, the oscillations are bigger and bigger. If you bring it to the point where it's almost continuous perpetual oscillation, then you take that picture, you look at the time between two peaks, and using the gain that you have and the time that you have found, okay, so based on the gain that you have, that you needed to take it to the perpetual oscillation plus the time between two peaks, you have various formulas that will give you proportional gain, derivative gain, and integral gain.
Okay.
And the most popular is Ziegler-Nichols. Then you have other names that frankly I don't remember, but they are all based on these two things. But it's very industrial process applicable. I don't think it's too applicable to robotics. It might be on certain things. So you can have this a way based on real systems. This is done directly on a plant that works. Then you have all the simulation-based examples, which is what analytical tuning, right? Which is similar to what we said before, that the example with the root locus is a possibility. Then you can go to stuff like where you find the gains that optimize something, a certain cost function, for example, and you go a little bit more into the optimal control. Okay, optimal control intended as we find the PID gains. In this example, we can do it so that this specific cost function, that is probably a formula based on the error in time and the control input through time generally, so that we minimize this formula when we have a step response. These are other ways. As we said, we can use the root locus, you can use loop shaping for a very underrated way. If you have to calibrate something on the plant directly, okay, if you have to tune something on the plant directly, is to think about it in terms of numbers, okay, is to use some logic, some reasoning. So you know that if you have a PID, your proportional component will be the error multiplied by a number, okay? So if we start super simple as that. And when I ask these questions, sometimes when I interview, and a lot of people say, where do we start from? And a lot of people say, we start from a little number. And I say, okay, well, what's a little number, right? It's 0.1, is 10, is 0.00001, and it's relative, right? And it depends on what your control input is, because if your control input is a percentage, it could be a percentage, right? The torque you give to the wheel, maybe it's a percentage because there is another system in between. So if it is a percentage, when your error and your maximum speed that you want to control is 2, worst case, you will have an error that is 2. What do you want your control input be when your error is the maximum? You probably want it to be relatively high, right? So if you start from 1, you'd go at 2% when your error is the maximum, which probably is too small. Okay, so these things you can think about. And the same on the integral, you can say, okay, if I have a 1 meter per second error for 10 seconds, that integral bit will be 10. Then I need to multiply it by something. So if for 10 seconds I have this error, how much do I want my control input to grow? So you can think about these things to have a stake in the ground, basically, and start from a certain point. And this is one thing. And the other thing I wanted to say is take a look at robustness, even in the basic way of phase margin and gain margin. But take a look at that when you have done your tuning. Maybe you have done your tuning live using Ziegler-Nichols or this logic approach, or simply, as you said, you start increasing your proportional up to a number, it works well, you're happy. If you have some sort of transfer function for your system, put your numbers in there, put your controller as you have designed it in there, have a look at least at the body diagram to have an idea of phase margin and gain margin, because they will give you the feeling of how close to instability you are if you have perturbations to the model, okay? Because maybe you have designed it it works well, but then you put 100 grams on the top of the robot because you add a sensor, and your response start going like bang, 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 because it's close to instability in that sense. Or maybe you add a small delay to your control loop because you change your sensor, you change your processing, so you shift the phase, and you have instability again. So that's a good way. Not many people look at that, but it's important.
Okay, that's a quite thorough explanation. Interesting. When we are working in a system where we have multiple set points, for example, a drone scenario where we give velocities, and with the help of feedback through the sensor of IMU, we have a goal in 3D, XYZ, we have to reduce that. So it's a goal. So from control system perspective, we have to reduce 3 errors at the same time. Okay. Mm-hmm. So how do you look at it? Because first approach is we can apply 3 PIDs, but how do you progress towards it? 3 PIDs, let's say they are not working. What should be the next step?
So we are talking about, we have 3 things to control, and we have 3 inputs, right? 3 control inputs.
We have just the velocity, but we have 3 errors based on XYZ axis. So we have to go at a certain point in XYZ axis, and sort of that scenario. We have velocity of the drone. Just let's make it simpler. Yes, we have 3 controls.
Okay. So if you have 3 control options, it's a multi-input, multi-output system. As many inputs and the same number of outputs that you want to control. So when you have these, the obvious solution is you identify which input you should use to control which output. So essentially you try to make it a single input, single output. You try to turn it into 3 single input, single output systems. Okay. And I think this should be the first attempt. For me, generally is the first attempt, because if you can stay single input, single output, it's easier. You probably have interaction between the 3 channels. When you actuate actuator number 2, you probably disrupt a bit system number 1 and system number 3, right? Because there is interaction across the channels. If that interaction is not too much, you can remain in a decoupled situation, and you keep it as 3 different systems, and you try to do your analysis on each system. To make it easier, if you still see a way to go along that line, you can try to make them decoupled in frequency a bit. So the example is you give them a different response in terms of how fast they are to respond. Okay, so you try to make one very fast, then you have another one that is slower, and then you have the third one that is even slower. So they don't really disturb each other. So you can artificially try to put a bit of decouple in the system in this way. Okay. Then if you have to go to a multi-input, multi-output approach, there are techniques for that are similar. If we're talking about linear systems, that they are relatively similar to what we have discussed before, just in a multidimensional space. Okay. So your transfer function is no longer one transfer function, is 3 times 3, because you have a transfer function from each input to each output, if it is all linear. And for that, you can use relatively traditional methods of linear control around multi-input, multi-output. There is H infinity is an approach to synthesize controllers, and is quite inherently multi-input, multi-output. So it doesn't really care if we are talking about single input, single output, or multi-input, multi-output. And it tries to minimize. It's a robust control-based approach. So it tries to maximize some norms to make the control system respond well in a certain frequency band, and to minimize other things that make the noise rejection good. So keeping it simple. Or you can go to model predictive control potentially, which is another way that is very inherently multi-input, multi-output.
Okay.
But you need a very good model for that. You need a very, very good model, and you need quite a lot of computational power.
A very good model in the form of the robots model, right? Dynamics model.
Yes. So what model predictive control does is it knows the model of the system. Okay, so the model of the robot in this case, it knows what the set point is, so where you want to go. If we are talking about the robot, the same mobile robot, for example, your set point in this case could be a position and a speed even. So you want to go to a certain position and have a certain speed. Model predictive control will find the optimal trajectory in time of the torque that you give to the wheels. So it will simulate the next 30 seconds, for example. It's up to us, but let's say 30 seconds of what the robot will do, so that you minimize a certain cost function that is probably the quadratic error with some information about the torque that you are giving to it.
Okay.
It will find what the optimal torque in the next 30 seconds is. Then it takes number one result, so the first part of that, and applies it. Then after one, we go through the cycle of the CPU, right, of the controller, and then at the next step, it does it again. But it will be in a different position, right? So it will have a slightly different result. I think a very good thing with MPC is this inherent multi-input, multi-output nature and how it handles constraints. A big downside of linear controllers generally is that they don't really understand that they have a limited authority on the control input. Okay, so a linear controller thinks that if you can go to 1 meter per second in 1 second, you can also go to 10 meters per second in 1 second if you give 10 times the control input. And if you give 100 times the control input, you can go to 100 meters per second in the same time. Because it doesn't understand that probably you have a limitation on the maximum torque that you can give to the wheel. It's linear, right? So because it's linear, and it doesn't know it.
Okay.
Model predictive control, you can tell it you have to minimize this cost function, and your limits are that your maximum torque is 1 Newton per meter, and you can also tell it your maximum speed that you shouldn't exceed. You can tell it various things, and it's very good at handling constraints. But it's computationally intensive because you understand that you have to run at some time in the future. You have to simulate your system for n times, and you have to do it a lot of times because it's running an optimization. So it tries a trajectory, it doesn't work, it changes the trajectory slightly to minimize this function until it thinks it's found the minimum of that cost function that you have given. So it's computationally intensive.
So we're looking at things from the student's perspective. On the career side, we have bachelor's, master's, and PhD in control systems. When they come to industry, what do you expect from them at all of these three levels when you are hiring them?
Okay, I think the way we look at degrees is on the countries as well. I think there are countries, for example, that almost see PhDs as expensive and maybe they are almost a negative thing. But I've seen that in some cases. Generally speaking, I try to look at experience. I try to lump everything into experience. Okay, I don't really care about the certification. If you have a PhD, think you are not the right fit for the position because you have not the right skills, or maybe I think you demonstrate to me that you will not learn the right skills. I prefer probably a bachelor that has demonstrated they can do the job and they are the right fit and they have the right attitude. So I don't think degrees make you better because you have the piece of paper. I think degrees should make you better because you have learned something. So if you have learned something, you can show it to me, and then the PhD or the master has made you better as an engineer. But it doesn't automatically make you better because you have it. And for the expectation, I think it's more what I expect depending on the position we are after, right? So if we are after a junior position, we expect certain things. And if someone with a bachelor or with a master applies, we expect the same thing more or less because it's still a junior position.
So should I give you some scenario of project that you can then give sort of level like mid-level, junior level, senior level, okay?
Yeah, let's try, yeah.
So as an example, a person implemented a closed loop system using PID controller for stabilization of the drone. Initially designed an open loop and we thought that open loop will help, but it led to steady state errors, and due to window disturbances, we incorporated feedback from IMU and GPS, and then feedback loop helped us stabilize the drone. And also, the drone feedback allowed us to adjust its position in real time, reducing the overshoot and improving stability. So if someone gives this description about his experience to you in a job interview, what would you rate it to be? Junior level, mid-level?
I think I already probably rated mid-level, with the caveat that I would like to understand how much they have done in this project, okay? Because if someone has done everything in the project, as in they have selected the components, for example, to build the drone, they have chosen the components, they have assembled the components, they have designed the electrical schematic, assembled everything, chosen the microcontroller, programmed it with all of these, I think this is pretty high level already, probably mid-level, I'd say, okay? Because it's a very broad experience in the end, right? So that's what matters to me. What I like is generally people that can do a bit of everything, and not people that can only do the MATLAB Simulink model, for example, or the MATLAB Simulink model, or the Python model, or the XCOS model, whatever, right? But they don't know any coding and they don't know any electronics. But this is, I think, is a slightly startup versus big corporation approach, right? The more you go towards big corporations, the more they have well-defined boundaries between positions. The more you go towards small companies, you have to do what's there to do, right? So it tends to be more broad.
Okay. Simone, thanks for your time. It's a lot of information that I have to absorb, and the time that you have given, you have been very generous, and I'm feeling an honored person to have you on the podcast. So is there anything that you want to add and advise to the people listening?
Thank you for having me, of course, and I hope it was useful, and I hope it will be useful to the people listening. And I'd like to know if there are specific things the audience would like to ask. I am open to have another go and try to, target specific topics if I can, okay? Always if I can. And in terms of what I want to say, I think I want to reiterate the part about playing around with things. Whether they are real things, if they can be actual things, I believe hands-on experience is invaluable. It's always invaluable. If I think about when I learned the most in my career, it's always been when I had to do something that I didn't know how to do, and I had to try and make mistakes and try again. The tipping points, okay, they have always been on those things. So yeah, the power of learning by doing, and even if you haven't the opportunity to do things on actual robots, plans, as I say, do your own simulations until they make sense to you. So for example, make a super simple dynamic system, but that is your system, okay? You have put it together, and try to apply a PID, try to tune the PID using a certain method, and then another method, try a root locus, try a body diagram, try an H infinity if you want, try an MPC, all on the same simple system. Even if it is simple, it will give you a lot of insights. We tend to find a lot of education that is about very complex things to start with. Okay, so if you try to understand MPC done on a 12 degrees of freedom robotic arm, it's harsh. But you can try it on a one link, okay? It's still a system, and if you try it on a one link, it's a lot simpler to get the gist of it.
Definitely. Very important thing to look forward. Do not get into complex things and try to learn from those. Keep things simple. Important thing is your learning, not the complex systems. Again, Simone, thank you for your time. I'm really happy to have you here. Take care.
Thank you, Lukman. Thank you very much. Take care.